A few people have already joined us. Let's give them a few more minutes. Okay, people are coming. Okay, should we start? So, good afternoon, everyone. My name is Francesco Petruccione. I'm the interim director of NITheP, and I have the pleasure to introduce to you for the fourth time in a row, Dr. Sahal Yacoob, who will today give us the last lecture in his introductory course on elementary particle physics. And I think today will be very special because he's at CERN. Yeah, and so he will give us the latest from the experimental scene from CERN. Sahal, we are very happy to have you again in our mini school, and we are happy that you managed to reach Switzerland or France, wherever you are exactly at the moment, safely. And we are really looking forward to the lecture that concludes the third lectures and the lecture on neutrino physics that we are all very much looking forward to. So Sahal, thank you very much. If you would like to share the screen, you are welcome to start your presentation.
Okay, thank you very much. Ilya, can you confirm that the sharing is working and that I can be heard?
Yes, everything is working.
Yes. And sorry, I always forget to encourage the participants to use the Q&A facility to ask questions. And I sometimes forget to introduce Dr. Ilya Sinaisky, who will coordinate the question session. Sorry for that. So please, Sahal, if you would like to start.
Great. So we're going to finish up some of what I didn't quite get to at the last lecture. I want to remind you of what color is. This is the charge of the strong interaction. And it has 3 charges. So there are 3 charges in the strong interaction. I mentioned this previously, just like the electromagnetic interaction has positive and negative. In the strong interaction, there's green anti-green, red anti-red, blue anti-blue. And in one of the earlier lectures, I think I introduced the omega baryon to you, which is a bound state of 3 strange quarks. So it's S, S, S with total spin equal to 3/2. And the reason I mention that now is because quantum mechanically, for this to be a spin 3/2, each of these quarks is spin 1/2, so their spins are aligned. They are the same quark. And so we get into a bit of a problem with the Pauli exclusion principle by the fact that this particle exists, because it looks like we have identical particles in the same state. Each of these strange quarks has a spin with projection 1/2 in the same direction. And this, I'm not going to say anything more about it in this slide, but this is one of the pieces of evidence that the color charge has 3 values, because in this case, we can break the degeneracy by giving each of these quarks a different value of color. And then we're back with an anti-symmetric wave function, which is what we need. But more experimentally, we can look at something like this. So this is an Feynman diagram in our standard format that I've introduced to you: two incoming particles, P1 and P2, two outgoing particles, P3 and P4. And in this case, the incoming particles are an electron and a positron. There's a mediating particle here, which would be either a photon or a Z boson in this interaction. And then what I've drawn here is that this photon and Z boson then decay into a quark and an anti-quark pair. But that did not have to be what happened. This could also have been to a muon or an anti-muon. And this is exactly the same diagram. So these are all interactions that take place within, well, electromagnetically or the electroweak force, depending on whether it's a photon or a Z boson. And the only thing that can change between the final states being either a muon or a quark are the charges. Remember, a muon has charge -1 for the muon and +1 for the anti-muon. And then the quarks have a complicated structure where the up quark would be 2/3 and the anti-up quark would be -2/3. The down quark would be -1/3 and the anti-down quark would be -1/3. So maybe I should write that down. Remember, we have our quarks that are UCT and DSB, and these are charge +2/3, and these are charge -1/3. Something else that's important is that these first two quarks are very light. Then we have the strange quark, then the charm quark is heavier, the bottom quark is next in mass, and the top quark is super, super heavy. And if you're reading ahead to the bottom of the slide, you'll see why that's important. But if we look at the cross-section for our incoming state of two electrons to produce hadrons, which are bound states of quarks, so this is quarks, to hadrons going to muons, then the only thing that matters that comes into the calculation in this ratio are the charges of the quarks. Okay, so this formula here is the cross-section for this process, depending on the charge of the final state particles. So when Q equals 1, this is the cross-section for production of muons. When Q equals 2/3, it's up quarks. When Q equals 1/3 or -1/3, but there's a square, so it doesn't matter, they're down quarks. If we want to use the strange quarks, it's another third, etc., etc. And so when we take the ratios, all that's left are the charges for the hadrons. There's another limit, and that's the energy at which the collision takes place. If the energy of the collision is too low, so we can't produce two strange quarks, for example, then we'll only produce up, down, and charm quarks. When the energy gets above the threshold for strange quark production, we'll produce all four of these quarks, but not the top and the bottom. And when the threshold increases more, we'll start to produce bottom quarks as well. So if we go through that and calculate what we expect for this ratio, okay? So it's the ratio of the number of produced quarks to the number of produced muons. If our energy is less than twice the mass of two charm quarks, we get a value of 2. As we pass the threshold for the mass of two charm quarks, we go up to 3.3. And then as we pass the threshold for producing bottom quarks, we go up to 3.67. You can work through this maths on your own, and again, send me an email if you can't get there exactly. So on the next page, we're going to see the results of just such an experiment. Before we get there, actually almost forgot the most important thing about this, is this overall factor of 3 at the front. And that overall factor of 3 needs to be there to account for the colors, because muons don't have color. So we can only produce a muon and an anti-muon. But if we're producing an up and an anti-up quark, we can produce a red one, a green one, and a yellow one. And the probabilities for producing each of those is exactly the same. So the cross sections for those are exactly the same. And so for each color, we get a factor of 3. And that's why we have this factor of 3 out in the front. And that's the big thing we're looking for when we look at the data. So here we're looking at the invariant mass of pairs of leptons from an electron-positron collider. These peaks are where there are resonances, so unstable particles that are created and then decay. This is the Z boson, up at about 90 GeV. Down here we have the Psi2S and the J Psi. The J Psi is where we turn on the charm quark production. The easiest thing to see, if I flip back, is the 3.67 and 3.33. But if we go along, there's 1, there's 2. So we start seeing data here consistent with 2. Then we produce the J Psis, and we have a bit of a bump, and we go up to our 3.3, but it's a bit messy because we have this other particle produced there. But we get up here finally to a nice 3.3 here. So let me go back again to 3.3 and 3.67. So we have our 2 band, then our 3.3 band, and then our 3.67 band. So our data is pretty well described by this idea of 3 and of 3 colors. And so if we didn't have this factor of 3, we would not be able to reproduce the data with this. So these are 2 items that I wanted to go through, which are why we are certain that the color charge has 3 distinct charges. And that's it for that. I'm going to go on to talk about neutrinos next. So I think if there are any questions about that, it's best to take them now.
Sir Sahal, can I ask a question?
Yes. I don't know. You have to ask the moderator.
Just a quick one. You take a ratio of the hadrons to leptons, but is in the electron positron going into the not muon anti-muon, but in tau anti-tau lepton? Is that also in that ratio?
No. So this is just the ratio to muons, right? So remember, we can choose our final state, and muons are easy to measure.
Okay, so kind of if that is happening, you're just not accounting that on the graph. So if there is the electron positron into the tau anti-tau, you are just not measuring that.
Yeah, we just don't care about it for this. I mean, it has been measured, but it doesn't help to measure this. Taus are very hard to measure experimentally.
Okay, and there is I think, a question from Inge. Let me allow him to talk, and he can ask his quick question before we go to the neutrino oscillation.
Yeah, my quick question is, if you look at basically that's the evidence of 3 colors coming from the, when you fit this whole curve, if you show the next slide, yes. If you show this slide, and if you fit the whole curve, and then suppose if there's only 1 color, then the whole curve should be sink down by a factor of 3. Is that where it come from?
Yes,
Okay.
except for the peaks. So the peaks are described by actual resonance shapes, but the flat bits should all be lower by a factor of 3. Yeah.
Right. Okay. Thanks.
Okay, great. Let's go.
Okay, so let's try to get to the end of neutrinos, the little neutral particles. I think neutrinos are very fun. So neutrinos are incredibly light. They have a mass that we know is greater than 0, but less than 2.3 electron volts, and they are electromagnetically neutral. So they're the only fermions that we know of that are fundamental and have no electric charge. They only interact via the weak interaction. That's the same as saying that they have no color charge either. They don't feel the strong interaction. And they were first postulated due to observations in the beta decay energy spectrum, which seemed to exhibit non-conservation in angular momentum and energy. Again, going through it, I hope this is not too boring for everyone. Initially, beta decay was thought of as being a proton going to a neutron plus a positron. At the fundamental level, we now know this is the weak interaction, with the U quark becoming a D quark, emitting a W boson, which then decays to a positron and an electron. That is wrong. I have 2 antiparticles there. So let me quickly fix that. I am so sorry. And that should be a V or a nu. So that one is the particle, because the positron is the antiparticle. So it's a positron and an electron neutrino. So if we consider the initial thing that we saw with a proton going to a neutron plus a positron, if the proton and neutron are both at rest, then we expect the positron to have a well-defined energy which is equal to the difference in the masses of the 2 particles. So we'll look at that and see that actually that's not the case. I also mentioned that there's an angular momentum consideration. The angular momentum of a nucleus is integer for an even number of nucleons and half integer for an odd number of nucleons. When we have beta decay, a proton becomes a neutron, so we're not changing the number of nucleons. So the spin of the nucleus doesn't change, but the positron coming out has spin a half. And that appears as a violation of spin and angular momentum. So if we look at the energy consideration, what we would expect to see is a spike here at E equal to MP minus Mn. So we'd expect a delta function there. What we actually measure is, as a function of energy, there's a continuum of the positron energy. And a way to account for this is that there is another particle in the decay that's carrying some of the energy away. And this was basically the beginnings of the idea of there being a neutral particle also being emitted in beta decay, and it's weakly interacting, so it's very hard to decay. So neutrinos are often inferred rather than detected. By inferred, I mean we see something missing, we see missing energy or missing momentum and attribute that to the neutrino. That makes them experimentally challenging and exciting. So zooming ahead to the evidence that led to the ideas of neutrino oscillation, we think we understand stars really well. We understand what happens inside a star. So given the mass of a star and its brightness, we can tell a lot about what's happening. So in our understanding of what's happening inside the sun, we are reasonably sure that all of these processes are taking place. I'm not going to go through all of them, but I am going to highlight that in a lot of these processes, we have neutrinos being produced. And these neutrinos are produced with high energy, and they leave the sun and come to us. And one of the ways of validating that we understood what was happening within the sun was to attempt to measure the neutrino flux from the sun and compare it to calculations. This was first done in 1968 using the reaction shown here on the bottom right. And immediately there was a problem, hence the title of the slide, the solar neutrino problem, where the solar neutrino flux was measured to be 1/3 of its predicted value. So that was a bit of a problem. And that was resolved with the idea of neutrino mixing. So remember, the experimental limits on neutrino mass are currently that the mass is greater than 0 and less than 2.3 electron volts. If the mass is greater than 0, and only if the mass is greater than 0, something called neutrino mixing is possible. And what neutrino mixing is when a neutrino of type I becomes a neutrino of type J, where I and J are equal to muon, electron, or tauon. And this happens if the basis we use, the quantum mechanical basis states that we use to describe neutrino interactions are not the same as the basis states of the Hamiltonian. So neutrinos only feel the weak interaction. So the states in which they interact are their flavor states, the ones I've been talking about, nu E, nu mu, nu tau, and they have definite couplings to the electron, muon, and tau, or rather to the W boson. If we look at the Hamiltonian for the system, we need mass eigenstates, and we call those mass eigenstates nu1, nu2, and nu3. And if the mass eigenstates and the flavor eigenstates are the same, then we have a situation like for the electron, where everything is consistent. In this case, they're not the same. So the mass eigenstates, right, the stationary states of the Hamiltonian for neutrinos are not the same as the interaction states. And this leads to neutrino mixing because neutrinos are created through their interactions in a flavor state. But once an electron is created in state nu E, it is a mix of the different mass states. It then propagates in time in these mass states. And so it's some fraction nu1, some fraction nu2, some fraction nu3. They propagate slightly differently. And then when we measure them again, we measure them in the flavor state, and we don't get exactly what was produced. It's a little bit complicated, so let's look at a simpler treatment of this. Let's consider just two individual states. So let's say there are two neutrino species. They have flavor eigenstates nu E and nu mu, and mass eigenstates nu1 and nu2. Then we can write down the electron neutrino as some portion nu1 and some portion nu2, the muon neutrino as some other portion nu1 and some other portion nu2. Don't be scared off by the trigonometric functions. The reason we use those is to maintain unitarity. So sines and cosines have the useful feature that when you square them and add them together, you get 1, and that the cross terms are 0. And that helps us just ensure that at no point are we producing more particles than we started with. So they're just there to help with the normalization. The mixing angle is a free parameter in our little neutrino oscillation model. So we start with a pure nu E state in this case. So we have produced in the flavor state nu E, which is some portion nu 1 and some portion nu 2. We let those states evolve for a time t, but because when they're produced, they have a well-defined momentum, and that momentum is consistent, and E squared is equal to P squared plus M squared. If the momenta are the same, but the masses are different, we have two different values of the energy, E1 and E2. So sometime later, we'll have the wave function described this way, and the neutrino that we started with as an electron neutrino is no longer 100% an electron neutrino. Here's our final evolved state. And then if we want the probability of measuring that as a tau neutrino, we take the square of the absolute value of the BT term, which is written out here. If we wanted the probability of remeasuring exactly what we found of an electron neutrino, we would take the AT term here. So these are just the coefficients of the electron flavor state or the muon flavor state that comes directly out of writing in an electron state here, for example. So we could complete the bracket. And we see a few interesting features. One is that the rate of oscillation depends on the energy difference, which is essentially the mass difference. So we gain a couple of things. We need theta 1, 2 to not be equal to 0. We need the masses to not be exactly the same. And in those cases, we can get neutrino oscillation. And to cut a long story short, that is what we get. If we make some assumptions, we can write things out explicitly in terms of the difference in the masses. So this is just some definitions that I'm not really going to go into in much detail, but they're there if you want the details. And so that idea of neutrino oscillations, because of the flavor and the mass states being different, possibly leads to a resolution of the solar neutrino problem. Actually, it does, and I'll show you those results on a later slide. There was a second neutrino problem, and that had to do with atmospheric muon neutrinos. High energy cosmic ray protons hit the top of the atmosphere producing pions. These pions decay to muons. The muons then decay to electrons. And in this chain, we end up with two muon type neutrinos and an electron neutrino, regardless of whether we produce a pi plus or a pi minus. So if we measure these, we should be able to measure a muon to electron neutrino ratio of 2:1. What was done is in Japan at the Super Kamiokande detector, they placed a detector and they measured the signal coming from the upper atmosphere and the signal having passed through the Earth. And if they measured exactly the same thing, then we'd say there's no muon oscillation. When they measured them different, if they measured them to be differently, then we would say that because from the top of the atmosphere to the detector, we have a short distance there and a long distance there, this can be explained by muon oscillations, because we oscillate depending on the length we've traveled. That length comes directly from this time coordinate. So this difference in lengths that our neutrinos have to travel leads to an experimental observable that we can measure. So if there's no oscillation, we expect to see a 2-to-1 ratio coming from above the detector and a 2-to-1 ratio coming from below the detector. If there are muon oscillations, we still expect a 2-to-1 ratio coming from above the detector. Built in there is the assumption that the neutrinos are being produced too close to the detector to have enough time to oscillate. And this 2-to-1 ratio is going to validate our production model for what we expect to see. And then anything besides 2-to-1 coming from below is going to be evidence of neutrino oscillations again. So this was done at Super Kamiokande, and they observed 2-to-1 above and about 1-to-1 below. This is showing a little bit of how this detector works. It's a giant tank filled with liquid with photomultiplier tubes on the edge. Each of these little hemispheres is a PMT. And as the neutrinos came in, they collided with the molecules of the liquid, accelerated them, and as those charged particles moved through the liquid, they produced Cherenkov radiation. So they emitted light, which was then detected in the detector in these circles. So that's really cool. And if you get the PDFs and click on the word here, there's a link to Super Kamiokande talking about using neutrinos to do astrophysics. After that, we had beamline experiments, which confirmed the oscillation of neutrinos. So a beamline experiment is something where we produce neutrinos in a well-controlled way, and we can tune the lengths and the energies to really hit these measurements and measure the parameters, the angles, and the mass differences. Here's a bunch of values. I'm not really going to talk about them. There is one last thing I want to talk about, and that's called the mass hierarchy. We know neutrinos have mass because they oscillate. So that's the cool thing about this whole idea, because for a long time, neutrinos were predicted to be massless because they hardly interacted and they appeared to be moving at the speed of light, as far as we could tell. The neutrino oscillation parameters are only proportional to the difference in the masses squared. And so we know delta M1, M2 and delta M2, M3, but we don't know which way the neutrino masses are. So this is something that's shown on the bottom left here. This is the normal hierarchy where nu1 is on the bottom, nu2 is in the middle, and nu3 is on the top. And these are the different mass states. And while we don't know their masses, we know from the research we've done that nu1 is the one that is mostly electrons. nu2 is the one that's kind of a third of each of them. And nu3 is almost 50% muon and 50% tau. But we don't know which one of these is the lightest. So we could have mu1, mu2, mu3 with the masses going up, or we could have mu3, mu1, mu2 with the masses going up. And those are called either the normal or the inverted hierarchy. We don't know which one of those is real. That's one of the active areas of research. And then finally, for the solar neutrino problem, the Sudbury Neutrino Observatory definitively established that neutrinos change flavor and therefore have mass. And they did this by measuring neutrinos in 3 separate ways. They measured the number of electron neutrinos from the charge current reaction. And then they used these other 2 reactions, the neutral current and elastic scattering reaction, which is sensitive to all 3 flavors of neutrino. And what they got was, when they looked at the charge current reaction, they reproduced the original observation of only a third of the flux being there but when they measured the neutral current and elastic scattering reactions, they recovered the flux that was predicted from the sun. And so these measurements, and they're highlighted in this paper that I've linked at the bottom, these measurements showed that if you just measure the number of neutrinos hitting the Earth, we get the right amount that we expect from the sun. We expect all the ones from the sun to be electron flavored, and they're not. And those two facts together basically solidified the idea that we understand the sun at this level and that the neutrinos being produced there are oscillating, and this led to the award of a Nobel Prize a few years ago. And that's it for neutrinos. I have a slide on what else is happening. I have two slides on what else we're trying to do in particle physics. One idea that we really like is unification. Everyone here, I'm sure, is aware that electricity and magnetism are pieces of the same force, but we once thought they were separate. The weak force was then unified with electromagnetism to give us the electroweak theory. A grand unified theory would combine the electroweak force and quantum chromodynamics. And we hope it's there just because historically we've seen this happen, and it makes things simpler. And generally, in the reductionist view of the world, the simpler we can make things, the more we feel like we understand the universe. And then on top of that, unification of gravity into a grand unifying theory, something that's called a theory of everything, is kind of a holy grail for many people. And string theory is currently the most promising approach of unifying gravity into this framework, but so far it's experimentally not very testable. So what are the unanswered questions we still have? I've just mentioned unification and theories of everything. We still don't really understand why, if the universe behaves the way particle physicists and astrophysicists think it does, there's no antimatter in the universe. We see lots more protons than antiprotons. And we don't have good candidates for dark matter and dark energy. So I appear to have rushed today. I'm sorry for that. I'll take your questions. I didn't want to run long as I have the last 2 weeks and then run out of time in the last section. Yeah, so that is it. Let me know if you have questions and if you want me to go over anything in more detail.
Yeah, Sahal, thank you very much for another excellent lecture. And Ilya will guide us through the questions. We had already a few, and I see that there are other people raising their hand wanting to ask questions, and Ilya will allow you to speak just now.
Yeah, go on, Inji.
Yeah, okay, Sahal, thanks for the very interesting lecture. I'm aware other people have questions, so I'm just going through my question quite quickly, just a few. One is, you mentioned about the nu2, which is the second mass eigenstate of the neutrino. And what is the, can you just repeat what you said? It's a mixture of what and what? And I remember you just went through that very quickly. The second, yeah, nu2, yeah. Hello? Can you hear me?
Sahal, you're muted.
Yeah, sorry, I could hear you, but I was muted. So let me go back a bit. So I introduced the theory simply here, saying we have 2 neutrino flavors and 2 neutrino masses. And that's a simplified model. The truth is we have 3 neutrino flavors, nu e, nu mu, nu tau. And so we need 3 neutrino masses, nu1, nu2, nu3, right? So these are the mass eigenstates, which are distinct from the flavor eigenstates. So nu2, this graphic shows you the blue bit is the proportion of nu2 that is nu tau, which is the flavor state. The red is the proportion of nu2 that's nu mu, and the yellow is the proportion that's nu E. And that's the color coding on all three of these. Does that help you?
Yes, that helped me. And my second is that neutrino can just oscillate in between the neutrino. It can't oscillate into anti-neutrino, right? Is that true? Is that what I said true?
Ooh, so that not using this formalism. That's right. So in
but
terms
I just wonder experimentally, did you see a neutrino oscillate into anti-neutrino? In that sense, there will be a 6x6 mixing matrix, isn't it?
Yeah, no, we don't see that. We don't see that. I have to think. So there are some very detailed, sorry, NG, maybe we need to talk about this outside of the lecture. There are CP violating interactions where we can see neutrinos become anti-neutrinos, but that's not this type of oscillation. So I think the correct answer to your question is no. This, the neutrinos oscillate to other flavored neutrinos. The anti-neutrinos will oscillate to other flavored anti-neutrinos, and things that mix neutrinos and anti-neutrinos are things that will have Feynman diagrams.
Okay, I see. And the next thing is that when you mentioned the 2-to-1 ratio, remember when you mentioned that experiment, can you just remind me what determined that 2-to-1 above? Yeah.
Yes, it's just here on the top line of the slide, right? If we look at a pi plus, when it becomes a muon, we produce a muon neutrino. When it becomes an electron, we produce an electron neutrino and a muon antineutrino. And these experiments don't differentiate between neutrino and antineutrino. So there's 2 neutrino flavored to 1 electron flavored for every pion.
So, okay, so and the chances that the pion decay into these 2 different ways are the same, so that the ratio between muon and electron neutrino should be 2-to-1. Right?
So every mu plus will become an E plus, and every mu minus will become an E minus.
Okay, I see what you mean. Okay, thank you. And the last question is, you show the measurement of the 3 mixing angle, theta 1, 2, theta 2, 3, theta 1, 3, and I presumably those are measured from different neutrino oscillation experiment. Can you explain?
Yeah. So a lot of these are done either in beamlines or built around nuclear reactors. So what you can do once you believe this is really what's happening is you have a very good idea of what electrons are going to be produced at a nuclear reactor depending on what power mode they're running in. And you can just build your detector at a certain distance. So then you're changing the length parameter, and you can measure these different aspects basically, right? So initially we saw this problem and we don't have much we can control because we are a fixed distance from the sun and we are a fixed distance from the upper atmosphere. But then once people start to believe in this, you can get money to build detectors around nuclear reactors and to build neutrino beamlines, and that's how we get these other parameters.
Okay, thank you. Yeah.
Okay, so let other raised hand to talk. That Ansley.
Thanks, Ilya. Hi, Sahal. Great lectures. I have 2 questions. Can you hear me?
Yes, I can. Thank you. Can you still see my screen, by the way?
Yes, I can.
Okay, great.
Okay, so I have 2 questions. The first is, are there any extensions to the standard model that predict specific neutrino mass hierarchies? And the second question is, empirically, what do we need to determine the neutrino masses?
Okay, so, sorry, remind me of your first question. Let me answer your second question and then remind me of your first question, just because I didn't write them down. So what do we need to predict the neutrino masses? So there are astrophysical measurements that work on predicting the sum of the neutrino masses. I know that they can do that, but I don't know exactly the details. In terms of particle physics, what we do to look for neutrino masses is we look at, see if I can zoom in. We look at the beta decay spectrum and we try to get really, really cold particles to beta decay into a really, really good detector. And we hope that we see the positron energy spectrum end, and then whatever is in that gap must be the mass of the neutrino. So the way we try to measure the individual mass of an electron neutrino is literally measuring the PT distribution, the energy spectrum of electrons coming out of beta decay or positrons coming out of beta decay, and trying to get over the experimental noise so that we can see that little bit. So particle physics wise, that's the approach. And what was your first question?
Okay, the first question was, are there any extensions to the standard model that predict particular individual neutrino masses, or are those?
No, they're all free parameters. The masses are all free parameters. We don't have anything that really predicts masses anywhere. So in the current standard model, the coupling to the Higgs field is arbitrary. It's experimentally determined. And in all extensions, as far as I'm aware, the masses are free parameters. I have never seen a BSM model that predicts fundamental particle masses. Yeah.
Okay, thanks.
Okay, so let me read a couple of questions because the participants, I asked people who wrote that question, they prefer if I would ask them. Okay, so one is, are there negative mass particles?
No, negative, remember the mass is energy in this case. So particles, the masses we observe of particles are basically a constant energy value that these particles have by their continuous interaction with the Higgs field. And so the observation of only seeing positive mass particles is the same as energy being a scalar that is limited as 0. So there are no negative mass particles for those reasons. I hope that makes sense.
Okay. Can you please clarify why the oscillations of neutrinos implies the existence of their mass? Can you please repeat it?
Yes. So let me find the right slide. Here we go. So if I look at this slide, and on the mathematical kind of base level, okay, so the probability, if the probability for an oscillation was identically 0, then there wouldn't be any oscillations. If the masses were the same, then E1 and E2 would be the same, because our neutrino is produced with a fixed momentum. And again, we go to E squared is P squared plus M squared. Okay. So if P is the same as M and M is the same, then E is the same, then this value would be 0. And we wouldn't see any length scale changes. So I guess mathematically, we could still say at this level, if the masses were the same, then we could still get some oscillation due to theta 1, 2, but it wouldn't change with distance. Wouldn't matter what distance we were looking at them over. So that's most of your question answered. So in order for them to have an energy difference, they need to have a mass difference. And in order to have a mass difference, they need to have masses. But we still have this thing that is left over. So we have to go back a little way because back even more, we need to have mass eigenstates that are distinct from the flavor eigenstates. So the whole treatment I presented to you depends on there being 3 distinct eigenstates of the Hamiltonian. And for those to be distinct eigenstates at a particular momentum or at rest of the Hamiltonian, they have to have different values of mass. And if they have different values of mass, then they each have to have a mass value. So the first thing I tried to do wasn't particularly conclusive because it couldn't rule out this theta 1, 2. But if we go back to the underlying theoretical underpinnings of this model, we need to have distinct mass eigenstates. And we can only have distinct mass eigenstates if we have distinct masses.
Okay, good, thank you. There is one more question. So I have read that they are working on detecting the dark matter particles. How can they do that while they don't know what the dark matter is?
Right, so what we know, what we expect from dark matter is that it interacts gravitationally. So the experimental evidence for dark matter has to do with looking at I think it's galaxy rotation curves, but you see things being in orbit around a mass that's not big enough to hold it in orbit at the speed that it's moving. And so the conclusion of that, after lots of work, is that there is something else providing mass that's holding these high-speed things in orbit, but that based on the forces, the interactions I've been talking about, we don't detect anything there. So the key element is that dark matter must interact gravitationally. And then you build experiments that look for gravitational interactions. So that's the first thing. The second thing is a more theoretical point. It's that we can put limits on what dark matter can be. Because when I make the statement that there's something that interacts gravitationally, but it doesn't interact with any of the other interactions we have, that just means we haven't seen that interaction yet. So then you can say, well, what's the limit on that, right? How much electric charge can dark matter have, or how much of a weak charge can dark matter have in order for us to not have seen it yet, but be able to see it in the future? And so when theorists build up models of what's still allowed, what can we fit in that fits with all the exclusions we've measured, but provides a massive particle that could be dark matter, then they put forward ideas and experimentalists try to rule out or look for those things. So the one thing would be to just use gravitational interactions to isolate a particle. And the other thing is theoretical extensions and to keep looking in the data for ideas for things that could be dark matter. I'm sorry,
Okay,
I'm not super happy with that answer. So I'm happy if there's a follow-up to help me explain it more clearly.
Okay, meanwhile, there is one more typed answer, and afterwards I will let Inge ask his other question. Okay, so in particle physics, which mass is considered gravitational or inertial?
Gravitational? I think that is a question I haven't thought about in a long time. I just think about it differently. So we ignore gravity. So it must be the inertial. Right, so that's the simple answer. In particle physics, we don't include gravity in this. And so the mass we get, our mass we get from the Higgs interaction, for example, is the rest energy mass, which is the inertial mass if you look at it from special relativity. And then you'll have to wrap your head around the fact that the inertial mass and the gravitational mass are the same. And that's where we get into general relativity, which is one of Einstein's big things. So as far as we know, we expect these to be the same, but since particle physics doesn't actually include gravity, then I guess the inertial is what we're looking at.
Okay, great. Inge, you can ask your question and unmute yourself.
Yeah.
Thank you.
Yeah, Sahal. Yeah, Sahal, you just two questions above that from other people's questions that you explain why there should be a mass difference between these mass eigenstates. But I find your argument is based on the assumption that the momentum is unchanged. As you show in the slides, if you reverse to the slides of the previously I think or later maybe there is a slide showing the showing that P is actually defined, but how can you guarantee in the experiment that the momentum is still conserved, so that the mixing is due to the mass difference rather than the momentum?
I'm not sure.
I mean, I think you have a slide.
When the particle is produced in the interaction, it is produced with a particular momentum.
Yeah, but when you propagate, I mean, I think if you just go forward to 2 or 3 slides, there is a slide showing that.
What slide are you seeing, Super Kamiokande?
No, the previous one. I think the previous one slide.
I'm worried that my slides are not updating when I'm changing them. What slide are you seeing me sharing? Right?
Now I'm seeing atmospheric Muon neutrino. Muon neutrino.
You want me to go forwards or backwards?
Backward, please. Yes. Okay. This slide. Therefore, if you see that paragraph, therefore, if theta 1, 2 not equal 0, and m not equal to m2, which would mean that E1 not equal because P is defined. So okay, I agree that P is defined in the momentum eigenstate, but how can you make sure that P is still constant when you measure neutrino propagating to such a large distance? If that P experimentally change, then E1 definitely not equal to E2, and that will not give you the evidence of M1 not equal to M2, because momentum can change.
So the momentum can change between the production and the decay. But this model is, so remember, at no point am I measuring the neutrino momentum, right? I'm just saying I've measured a neutrino. There is a neutrino here. The assumption is that when a neutrino is produced, it is produced in a well-defined momentum state. And I just think that is a true statement in my philosophical understanding of the world, right? And it doesn't matter what happens in between.
Okay,
really.
I see. Okay. The other quick question is that what do we understand the lepton conservation in the weak interactions? I remember there's, when you see these decay or a lot of these interactions, the lepton number is actually conserved, taking into account of these electron, muon and tauon, and also their neutrino counterparts. But do we understand why that lepton number is conserved?
No, we don't have a fundamental reason for it. I mean, there's a symmetry in the Lagrangian that protects it, but it's essentially just an observation.
Okay, thank you. Yeah, that's all my question.
Okay, that's all the questions. At least if nobody came up with any other question, I think Francesco, you can take over.
Okay, Ilya, thank you very much for coordinating the question session. And Sahal, again, thank you very much. And now I would suggest that all participants stay with us another hour so that we can do the exam. I'm just joking. But maybe in future we should organize a test or something so that we could give the participants a kind of a certificate of participation. So if you are interested in something like that, please let us know so that we can plan it in advance for the next mini schools. Sahal, thank you very much again for your time, and in particular considering that you're giving the last lecture from overseas. That's really much appreciated. Thank you very much. And thank you very much to all the participants for being so loyal to this mini school on particle physics and to the mini school concept in general. And in the NITheP newsletter that most of you must have received yesterday, and if you haven't, please register on the NITheP website so that you will receive it in future regularly. We already announced the next mini school, and we will send out a formal specific announcement for the mini school out tomorrow. And it will be about machine learning with quantum computers. So please be with us again next Tuesday, where we will start a new mini school. So thank you very much again to everyone. Thank you, Sahal. Thank you to the participants. And I'm very much looking forward to see you all again in a week's time. Thank you very much. Bye. Bye-bye.
Thank you all for coming. Goodbye.
Thank you. Bye-bye.